So this is 2025 paper 1 question 10, and we're basically given these patterns, and the next pattern, so we're asked to draw pattern 4, the next pattern is always going to be all the points that are 1 unit away from a point in the previous pattern when you read all that. So basically an example of that is if we go to pattern 3, see this red point here, that's a distance of 1 unit away from this point and this point, so therefore my little red dot, that is going to be in pattern 4. And they already give us a quarter of pattern 4, so you could just try to continue the pattern, or you can kind of draw them in on pattern 3 using a pencil, of course. And you can see that all these points are going to be 1 unit away, and all these points on the inside are also going to be a unit away from a black point, at least. For example, this point here is a unit away from this and this. So you can see that it's kind of just like a bunch of diamonds radiating outwards. So if you didn't spot that, you could just try to kind of symmetrically complete the pattern that we have here. So you can see that we kind of have these 3 in a line. So then we're going to continue and kind of turn that into a diamond shape as we saw above. And just fill in these ones. And then we can just fill in the outside diamond as well, like this. And you can also, as I said, draw out the points on the previous pattern and see if they line up. And as you can see, the red points that I drew in here do line up the same as the points that I drew in here. Then we're told that in pattern 2000, there are 4 points that are a distance of 2000 units from the origin. Write down the coordinates. So this seems pretty complicated, but I suppose a good thing to do if you're not sure of something like this is to see if there's any patterns you can notice in the previous ones. So basically, we see that here, what's the distance of these points from the origin in pattern 1? Well, you can see the distance of this point is 1, because this is 1, 0. Equally in pattern 2, we also have 2, 0, and that's obviously 2 units away from the origin. And then if we look at pattern 3, kind of ignoring my red dots, I'll rub them out now, you can see that we have the point here, 3, 0, and it's going to be a distance of 3 from the origin. And indeed in pattern 4, we also have the point 4, 0. So you could say, in general, in pattern, well, I guess you could write these down. So in pattern 1, we have 1, 0. In pattern 2, we have 2, 0, ... So then if we go to pattern 2000, we can just kind of continue the pattern that we're seeing. So we're going to have 2000, 0. And then again, if you look at these, we also have the points 1 or 0, 1. And then we have -1, 0, and 0, -1. And of course, these are all a distance of 1 from the origin because they're only on one of the axes. So we can kind of continue the same thing here. So we can write 0, 2000. We can write 2000, or -2000, 0, sorry. -2000, 0. And then we can have 0, -2000. And if you compare these again to these patterns here, you can see that here we also have 0, 2, -2, 0, and these are all going to be a distance of 2000 away from the origin. In part 3, we're asked to find the smallest value of n for which the point 4, 4 is in pattern n. So again, it's useful if if you're not sure what to do for a question like this, you'd kind of look at the previous ones and see if we can spot any patterns. So notice that this number is the same as this number. So let's go back and see if we can see any of the same things. So in pattern 1, we can't really see anything. I'm going to rub these out, by the way, just to make it more clear. So we have 1, 0, we have 0, 1 and stuff, so it's not super useful. But then in pattern 2, notice that we do have the point here, which is 1, 1. So we might want to keep a note of this on the side and say that in pattern 2, we have the point 1, 1. In pattern 3, again, we don't really have anything useful where the two numbers are the same. But in pattern 4, you notice here, we have the point 2, 2. So in pattern 4, we have the point 2, 2. And we can actually just we can kind of see that each time this number is going to be double of whatever these numbers are. And you could draw out the next few patterns to see that the trend continues, but you can just kind of assume this trend continues because the way that we draw the next one is kind of similar to the way that we draw the previous one. So that means that if we want 4, 4, well, that's going to be in pattern 8. And again, the reason for that, because 1, 1 is in pattern 2, 2, 2 is in the pattern 4. So you can see that this number is double whatever these numbers are. So if we have 4, 4, that should be in pattern 8. So therefore, you can just write n equals 8 and kind of show your reasoning by writing that down. So then we're told this information about a function q of n, which doesn't really matter for now. They basically just want us to rearrange this to write n in terms of t. So we can bring the 1 to the other side to get t minus 1 equals 2n, and then divide both sides by 2 to get that n is t minus 1 over 2. Then they give us what q of n is in terms of n, and they ask us to prove that this is true. So they want to get q of n in terms of t, and we know what n is in terms of t, so we can just replace all these n's with t's and simplify. So basically, we know that q of n is equal to n plus 1 the whole thing squared. So we can write that as t minus 1 over 2 plus 1 the whole thing squared over, and then we'll have 2n, so it's going to be t minus 1 over 2, and we have plus 1 the whole thing squared. So it's going to be a bit of a pain to simplify. I think the easiest thing to do here is to combine these fractions so that we don't, it's just a bit easier to work with. So instead of writing plus 1, we can write that as plus 2 over 2, because this is the same as just plus 1. And then if we have plus 2 over 2, well, that's the same as just, these both have the same denominator, so we can just add them like that. So then what we get is we're going to have t minus, or t plus 1, because minus 1 plus 2 is plus 1, over 2 squared, all over. And then here we're just going to have, so we're going to get t minus 1, because those 2's will cancel each other out, multiplying and dividing by 2. And then we have plus 1 squared, and then minus 1 plus 1, obviously they cancel each other out, so we just have over t squared. So now, when we're squaring a fraction, we square the top, so we'll have t plus 1 squared over 2 squared, all over t squared. Okay, so then we can continue simplifying. So t plus 1, the whole thing squared, will be t squared plus 2t plus 1. If you write out the brackets, that's going to be over 4, and then this whole thing is over t squared. Now, you could flip the fractions upside down, or however you do it, learn how to do it. The way that I prefer to do it is we want to get rid of this 4 on this denominator. So if we multiply the top of the fraction by 4 and the bottom of the big fraction by 4, we're allowed to do that because that's just multiplying by 4 over 4, which is just multiplying by 1. Well, then the 4, this, we're multiplying here by 4 and dividing here by 4. So what we're going to get is just t squared plus 2t plus 1 all over, and then on the bottom we have 4t squared. And that is indeed what they asked for. Then we're basically asked to find what happens as t goes to infinity. So the fastest way to do this is if we split up this fraction, it'll be a bit easier to see what to do. Or alternatively, you could divide everything by t squared, but I think splitting it up is a bit more straightforward. So you want to see what happens as t goes to infinity. And we're going to have t squared over 4t squared plus 2t over 4t squared plus 1 over 4t squared. And we can simplify this a little bit. So what happens as t goes to infinity? And then we're going to have t squared over 4t squared is going to be a quarter. And then we're going to have, this should technically be in brackets because the limit's on all of it. And then we have plus, we're going to have 2 over 4t, which is the same as 1 over 2t, but it doesn't really matter. And then we have 1 over 4t squared. So as t gets really, really big, this fraction gets really, really small. It actually gets very close to 0. So this goes to 0. This also goes to 0 when t gets very, very big. So all we're left with is just the 1 over 4. And you can verify this if you go to your calculator and you plug in bigger and bigger numbers for t, like start off with 99, then do 999, and then do 99999. You'll see that it keeps getting closer and closer to a quarter. And that's a way that you can verify your answer. And then this is how you show it. So yeah, that gives us our answer. Then we're told that h of n is the total number of dots in pattern n. So what's the value of h of 1? Well, how many dots are there in pattern 1? The answer is 4, so that's pretty straightforward. So then we're told this identity that h of n plus 1 is always equal to h of n plus 2n plus 3, and we're asked to use that fact to prove using induction that h of n is equal to n plus 1, the whole thing squared. So basically what we have to do for induction, I'm just going to go through the steps, not the visual reason of or how it works. So basically, the first thing we have to do is we have to see if our proposition is true when n is equal to 1. So our proposition is that this is true. So let's see if what h of 1 is equal to. Well, h of 1 will be equal to 1 plus 1 squared, which is equal to 4. And we know that's true from part I, or part 1, because we showed that h of 1 is equal to 4. So then our second step of induction is we assume that our proposition is true for some number k. So we're going to say assume true that h of k is equal to k plus 1 squared. And then what we need to do is we're going to have our proposition of k plus 1. Is this true? And the proposition for k plus 1 is basically the fact that h of k plus 1 should be equal to k plus 2 squared. Because it's k plus 1 instead of this k. Instead of this n, I suppose, we have k plus 1 squared, so that's just k plus 2 squared. So this is the proposition we're trying to prove, and we're assuming that this part of the proposition is true. So we know this fact here is useful. So we could say that h of k plus 1 is going to be equal to h of k plus 2n plus 3. And that was actually given to us. And then we know what h of k is from assuming that this is true. So we can just replace that. So h of k is just going to be k plus 1 squared. Sorry, this should be a k here because we're replacing all the n's with a k. So we have plus 2k plus 3. And then we can just expand out the bracket because we want to make this look like this because then that would prove that this is true. And we've done that from things that are true already. So we have k squared plus 2k plus 1. And then we have plus 2k plus 3. And then we can combine like terms and get k squared plus 4k plus 4. And we can actually factor this, because factors of 4, we have 2 multiplied by 2, and then 2 plus 2 gives us 4. So that'll factor nicely into k plus 2 squared. And that's what h of k plus 1 is. So we can say, therefore, the proposition for k plus 1 is true. And let me just write a little conclusion to show that we kind of understood the question. So we've shown that the base case p of 1 is true, so the statement is true for 1. And then we assumed that the statement is true for k, and that implies that the statement is true for k plus 1. So therefore, the statement must be true for all values of n in the natural numbers, because that's what they wanted us to prove it for, and induction only works for natural numbers. So that's the end.